In this video, we're going to talk about numerical integration. So I have three examples of things that we might try to integrate, such as sine of x squared, 1 over the natural log of x, and 1 plus x. I wrote squared there, but I meant to write to the fourth. So sometimes when we can't find a workable antiderivative for a function that we have to integrate, we can partition the interval of integration, and we replace the function by a closely fitting polynomial on each subinterval. So we're going to match a curve to the given integrand. Polynomials are very easy for us to integrate using the power rule. So what we can do after we've integrated that polynomial is we can add the results to approximate the definite integral of the function. So this procedure is an example of numerical integration. And in this section, we're going to study two models, both the trapezoidal rule and Simpson's rule. And a key goal in our analysis is to control the possible error that's introduced when we are computing an approximation to an integral. So more briefly, these are hard for us to figure out. If we approximate them with a polynomial, then we can integrate that polynomial easily and we can measure our distance off. So the first rule we're going to talk about is the trapezoidal rule. So if we have the integral on some closed interval from a to b of a function, and that function is something that is very difficult for us to integrate, well, the trapezoidal rule says that we can take delta x divided by 2 times all of these y output values. So y sub 0 plus 2 of y sub 1 plus 2 of y sub 2, continuing along, plus 2 of y sub n minus 1 plus y sub n. So you'll notice my first output and my last output are not doubled, but every output in the middle would need to be multiplied by 2. Delta x represents the length of my subintervals. So we take that entire interval from a to b, we find that difference or the length, and then we divide it by n being the quantity of subintervals. And as we talked about, especially when we're dealing with Riemann sums, the larger quantity of those subintervals there are, the more accurate your approximation will be. So if we, per se, we're looking at, say, 0 to 9, and we wanted to divide that into thirds, we would get 3, 6, 9. And that would be found, we said 9 minus 0 divided by 3 subintervals. That gives me that each of these spaces, delta x, would equal 3. So our x values, the x values that we would need to determine to plug in and get these output y values, those can be defined as our first x value, x sub 0 or x naught, our initial x value, would be a coming from the left endpoint of my interval, my least value. X sub 1 would be a plus that subinterval length, delta x, plus x sub 2 would be a plus 2 of those delta x. X sub 3 would be a plus 3 of the subinterval length, delta x. Continuing along to x sub n, which would eventually take us to our b value, b being the right endpoint of my horizontal x interval. So that's my description of the trapezoidal rule. Here's how it's written in your text. Let's do an example using the trapezoidal rule and see how our approximation is close to the exact value of an integral. In this example, we're going to use the trapezoidal rule with n equal to 4. We're going to estimate this integral. And then we're going to compare the estimate with the exact value. So we're dealing with the integral from 1 to 2 of x squared dx. And obviously this is very easy for us to calculate the exact value, right? If we were solving this, that would become x cubed over 3 from 2 to 1. 2 squared, I've got 8/3. 2 cubed is 8/3 minus 1/3, or 7/3. I have the exact value, right? So what we want to show is that we can use the trapezoidal rule with this function or any function to approximate that 7/3. And so we would use the trapezoidal rule in the situation where this function, our integrand, may not be easily integrable. So what we notice is that our interval length is 1 unit long, and we want to divide it into 4 subintervals. So my partition, I'm going to partition 1 to 2 into 4 subintervals. Delta x equals 2 minus 1 over 4, or rather 1/4. So we are taking the distance from 1 to 2 and breaking it into 4 equal subintervals, or 4 subintervals of equal length. So I'd have 5/4, 6/4, and then 7/4 up to 8/4. So let's recall what our trapezoidal rule is going to look like. T equals delta x over 2 times my initial y value, or my initial output, plus 2 of my y sub 1, plus 2 of my y sub 2, plus 2 of my y sub 3, plus my last value, y sub 4. So the first and the last terms aren't doubled, but all of the terms in the middle are. And those are calculated using these x values. So my first x value is 1, then I would have 5/4, 6/4, which is 3/2, 7/4, and then 8/4, or 2. So those are my x values, and I'm going to plug each of these 5 x values into my function. Those are going to give me my y output values. And plugging the 1/4 in for delta x, that's going to give me a 1/8 on the outside of this. So t equals 1/8. I've got 1 plus 2, 1 squared is 1, plus 5/4 squared, or 25 over 16, plus 3/2 squared, so I've got 2 of 9/4, plus 2, 7/4 squared is going to give me 49 over 16, plus my y sub 4, that's going to be 2 squared, or 4. And if I perform this calculation right here, I will end up with t equals 75/30 seconds, or roughly 2.34375. So this is my approximation for that function, for the given function x squared, using my trapezoidal rule. Now, we know what the exact value is. The exact value is 7/3, right? We did that right at the onset. So 7/3, how does that compare to my approximation? Right, so my exact is 7/3, or 2.3 repeating. So my approximation is very close to that, but it's just a little bit bigger. So the trapezoidal rule overestimates the integral by about 0.5% of its true value, 7/3. And the way we can calculate that percentage error is by taking the approximate value, subtracting from it my exact value, and then dividing by the exact value. So we can say the percentage error is my approximate minus the exact over the exact, or 2.34375 minus 7/3 divided by 7/3. And calculating that, we get 0.00446, or roughly 0.446%, which is pretty close to half of a percent. And half of a percent is a very, very, very small margin of error. So the only reason we use this very basic x squared function was because it kept our calculations up here simple. All right, this isn't something that we need to use the trapezoidal rule for. I'm just showing you that this is something we can use for a function that we can't integrate. Okay, so essentially all we're doing here is error analysis, and we're just trying to say how close can we get to where we're saying, all right, this is approximately the integral within a small enough region of error. In the next video, we're going to talk about using the Simpson's rule, which is a parabolic approximation, and it gives you just a tiny bit more of a precise answer.